Hello, welcome to another OMG video. Today we're going to be looking at first ionisation energy. Now our definition for first ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. In this one now, each time the outermost electrons is being removed, okay? So we're not taking any close, we're going to take the one furthest away from that nucleus. And our general equation, if I was going to take a general element, so I'm just going to say E, is E gas, turns into a positively charged ion because it's being subjected to an electron being taken away from it. Now, our energies are different for every element for first ionisation energy. So let's talk about what influences it. So the first major thing is the thing which holds an electron there is the positive attraction of the nucleus. We call that Z. Okay, so this is positive attraction. And this is governed really by the protons. How many protons in the nucleus? That's what governs that. But other things come into it. We've got something called shielding. Okay. We've got repulsion between electrons as well, because the electrons are both negative. They don't like each other sometimes. So that's what's going to influence first ionisation energy. Now we're going to first look at the trend across periods. Specifically, this trend which we're going to talk about is for periods 2 and 3. Okay, so we're talking either lithium to neon, or we're going to be talking about sodium to argon. Those are our two periods for which we can say these trends hold. Now, the first thing I want us to see is that we would expect the first ionisation energy to steadily increase across periods due to there being an increased number of protons in the nucleus, but this isn't the case. And from this graph here, we can see this isn't the case. We would expect a straight line. If you trace my lightsaber now, we would expect a nice, straight, steady line increasing. But we can see that at times the first ionisation energy is decreasing, even though there are an increased number of protons in the nucleus. So we're gonna pick out some real key highlights of this, key things for us to know. And just to remind you, this trend is exactly the same if instead of doing period 2, I had sodium and so on, all the way along to argon along the bottom. So they could ask you about period 2 or 3. You need to be aware that this trend is the same. So we're going to pick out our first key point. Let's pick out this transition here between lithium and beryllium. Okay. Now the reason that first ionisation energy increases there is that my number of protons has increased. I've got one extra proton because I've got one extra electron. And there's no shielding, there's no extra distance from the nucleus, there's no repulsion, okay? So that's why that increases there, okay? Now the huge one, first thing we need to know about is this dip here. And for that we're going to reference our electronic structures. Now if you notice for beryllium, its outermost electron is in 2s, but for boron we are now in 2p. Now, the 1s and 2s electrons are shielding that 2p1 electron from the nucleus. So, we've got shielding from the filled 2s orbital. Okay, we're taking our electron from an orbital which is shielded from the nucleus. Now, in this area where it goes straight now, again, we got no extra shielding, no real changes. The only changes happening is that there's more protons. So you would expect it's harder to remove that electron. My next big drop, and I'm going to use red for this one, is here. Okay, not as big a drop, but it's still something which we need to be aware of. Now this time, it's not to do with shielding, and we can see, look, for oxygen, it's still being taken from the 2p orbital. What is different here is that if I rotate the 2p orbital for nitrogen, they're all unpaired, whereas for oxygen, they are now paired up. Okay? Now, these two electrons don't like each other. They repel each other, in fact. And that makes it easier to remove an electron from oxygen. So paired electrons in 2p repel each other. And finally, we can see it steadily increase again. Yes, our electrons are pairing up, but this is no new story now. There's no new phenomenon, so it's just going to steadily increase again with the number of protons. Neon is the highest because it's got the most protons and it's in the same energy level. Now for the trend down groups, this is much more simple. There's no sort of unexpected twists and turns at this point. The first ionization energy decreases down groups due to there being an increased number of shells shielding the outer electrons from that nucleus. So we've got more barriers in the way for that positive nucleus to hold it there. Just to exemplify this, let's look at lithium and potassium. So for lithium, it's period 2. So that means it has got 2 shells. So I'm going to be taking an electron from where I'm putting a little yellow star. Potassium is in period 4, which means it's got 4 shells. 3, 4. I'm going to be taking an electron from here. All of these shells are filled with electrons, which also want to be attracted to that nucleus. They want as much of a fair share of that attraction, okay? So this electron is shielded more than this one. And this contains, so sodium's got 1 more shell than lithium, potassium 2 more shells, and so on. Here are some questions for you to try. So you can pause the video at this point. And here are some answers to those questions for you to check. So make sure you pause, get the correct answers. Thank you for listening. I hope to see you on another OMG video soon.